completely different. I'm not atomic physics, but it is laser physics. So how many people here really consider themselves laser jocks? I know there's a couple. Yeah, 3, 4, 10. So that's what you'll love this level test. So first, some references. I still, even though it's really old, I still like our original LCLS Conceptual Design Report, Chapter 4, which is available on the web, which is a fantastic FEM tutorial. Some of my slides come from there. Margaret Tondo has written quite a few things on a tutorial nature on this, and the person who is, the young person who's largely responsible for the FEL age from the point of view of theory is Jerome Huang and his mentor Huang J. Kim, and those guys have written on this too, so we can look at those things. So here's the outline. First, I'll say a little bit about radiation itself, how X-rays are produced, free electron laser basics, LCLS, and the growing list of X-ray FELs, but actually late last night I cut out the list of the growing list part because it would be too long. And then the future maybe, which I think, I hope, is attosecond X-rays with terrible per centimeter field strength. Okay, well, 1960, this is one of those Moore's Law plots, right? In fact, that's what this blue line is, Moore's Law. 1960, a lot of stuff started to take off exponentially. We all know about Moore's Law. Here's that wonderful slope that makes everything in information technology possible today. Here are X-ray laser, or X-ray peak intensities, not laser, X-ray peak intensities. And you see we've been on a torrid path in the last 50 or 55 years, greatly outstripping Moore's Law in how much brighter X-rays are becoming. So why is that? Well, beginning, it was just X-ray tubes. And then we learned how to use relativistic electrons in bending magnets. This was the era of the 1970s and the beginning of the synchrotron radiation sources. We discovered if we started, this is a wonderful story here, I won't have time to tell about how we went from bending magnets to wigglers to undulators. It was amazing. The reason that it worked is politically, because these were all parasitic sources on high energy physics synchrotrons, but the reason that it worked is that it made the electron beams colder, so that it actually made them brighter for high energy physicists. So they went from forbidding slack scientists like Herman Winnick to put wigglers in the storage ring to insisting that they put wigglers in the storage ring overnight. So we went from wigglers to undulators and then finally to FELs. 10 orders of magnitude between the third and the fourth generation, sometimes called a factor of 1 billion, which sort of underestimates it, but okay. Now, let's start with some basic physics. This is all a basic physics talk, which you'll be able to, I think, understand completely, and by the end, you'll be able to explain and tell your friends why free electron lasers are so wonderful. So let's look at an accelerated electron. Acceleration in a circle, synchrotron radiation is just the radiation that comes from electrons accelerating in a circle. Of course, the acceleration is always perpendicular to the velocity in that case. And if the electron is going around relativistically, this donut-shaped radiation pattern that we're all familiar with turns into a narrow beam with an opening angle of 1 over gamma. That's the relativistic gamma. So if you have a bunch of electrons in such a device, they emit radiation with random phase, and if there are n of them, you then get radiation intensity that goes up like n, and the number n in a bunch can be as high as on the order of 1 billion or so. Now, one of the things that really got synchrotron radiation going, even in the bending magnet age, is that this radiation source becomes very powerful if the electrons become relativistic. It's kind of amazing how it scales. Here's standard Larmor, K equals 1 for CGS, 1 over 4 pi epsilon naught otherwise. And if you take this acceleration and write it down for a relativistic electron going around in a circle, it acquires this gamma squared, and of course it's squared, which means that the power radiated goes like gamma to the 4th power. So should we increase the energy of a relativistic electron beam by 10, 20%? Yeah, every little bit. In fact, this tells you why the high energy physicists dropped electrons, because this radiation becomes a significant fraction of the energy circulating in the beam once gamma gets high. And so they needed to get to high energies without getting to such high gammas, and that was the reason. So that's it on bending magnets. You're now experts. Let's go to periodic magnetic structures. So here's the standard cartoon. These are permanent magnets. This is the pole, south, north, south, north, south, north. So you see the magnetic field is perpendicular to the direction of the electron motion, and then the force, and therefore the response of the electrons to this magnetic field is perpendicular to those two directions. So this is just the Lorentz force. It will wiggle back and forth. So such structures are called undulators or wigglers. Of course, what we're interested in now is the highly relativistic limit. So let's take a look at what's important. Of course, the electron energy is going to be important because that will, for one thing, determine the opening angle of the radiation beam that goes out there. It's the same thing as in a bending magnet. The wavelength of the light that comes out, the undulator period, are the two characteristic distance scales. The undulator period has to be something macroscopic because we have to be able to build it, although it could be something as small as optical, because the undulator could just be a laser field that's counter-propagating. That would work. But typically we use powerful permanent magnets with a few centimeter periods. The number of periods in an undulator is finite, so that number is capital N in here, and then there's a peak magnetic field, B naught. So the sort of first order thing is that there's a sinusoidally oscillating magnetic field. Here it is, and it's got a period of the undulator period. Okay? Now, an important parameter in this wiggling turns out to be how much it wiggles. So you could say amplitude, right? Let's see how much we deviate. But it turns out that the angle is a little bit more interesting. So let's consider in this sinusoidal motion the maximum slope of the sinusoid. Okay? So that's like the maximum angle of deviation. Since electrons are radiating in a direction that's more or less forward to their instantaneous velocity, just because of relativity, that angle then will tell us the angle of the radiation spray that comes out as a result of the wiggling. So K is the sort of normalized angle of deviation. It's not actually the angle of deviation. The actual angle is K divided by gamma. It's got that same 1 over gamma. So in the rest frame of the electron, which is going up and down like this, there's a relativistic shortening of the undulator, but in the lab frame, there's a relativistic flattening out of the wiggle. So K over gamma is that maximum deflection angle. So you can see, because we also have this 1 over gamma cone here for just the bending style radiation that comes out from a relativistic electron, you can see that there must be two important regimes. One, where K, this normalized K, is greater than 1. In that case, the radiation emitted on these beams actually falls outside this narrow cone 1 over gamma, so it'll radiate somewhat over a wider cone. Okay? And if that's the case, then radiation on successive bends won't generally add up coherently. And then the other regime is where the deflection isn't so large, it's within gamma, and in that case we have an opportunity for constructive interference. So in the right circumstances, you can get the power to radiate as n squared, and of course that's what we want. So this is the wiggler regime, this is the undulator regime. Physically these devices are exactly the same. You go from one to the other by changing the magnetic field, which you can do by changing the spacing, or by changing the energy of the electron beam, which is, I'm not even telling you how the accelerator works here. Okay? We've made those. Okay. Yeah?
Perhaps I missed it, but what is the physical significance of K?
K is the normalized angular deflection. So in other words, K over gamma is a physical property in the lab frame. It's the maximum angle of deviation of the electron. How do you control it? Well, you can see, you could control it by changing the peak magnetic field, which you could do by moving these magnets closer together, or we'd make it bigger. And because it depends also on gamma, you could change gamma. You could change the electrons. You could go from 15 to 10 GeV, for example. And K is a big deal. You know, These accelerator physicists, you know, we laser jocks, we have certain jargon that we just throw around all the time, and everybody knows it. You know, we say doubled, everyone knows what that means. We say red, everyone knows what that means. We say blue, everyone knows what that means. It doesn't mean what a standard person on the street would think. We know what it means. And these people use K, okay, all the time. Okay, so here's again, K, same K. I said you could get constructive interference under certain conditions. What conditions are those? Well, this is the most fun slide. This is where, oh, I get it. The relativistic electrons are almost moving the speed of light, but they're not moving in a straight line. They're wiggling. So even though they're moving the speed of light, they aren't actually going the speed of light. They are progressing down the undulator slower than the speed of light by some amount, depending on how much they wiggle. Depends on K, right? Depends on K. They also aren't truly, really going the speed of light. I mean, they are actually just going nearly the speed of light. As a factor of 1 over gamma there. So resonance occurs when the electrons slip one optical wavelength. By optical here I mean the radiated wavelength. One radiated synchrotron radiation wavelength, which I call lambda r, but actually someplace I call lambda 1, and I cut and pasted from Jerome's paper and used 1. I think it might be kind of a dyslexia thing, because we must have meant r in here. 1r. Anyway, so resonance occurs when the electrons slip one optical wavelength after each undulator period. Okay, so here's the wiggle, here's K over gamma. You can see what it is. And here are these guys going one period, they fall back one cycle. This is electric field down, up, down, one cycle. That's the resonance condition. Okay? And then you can get coherent addition over the undulator. You can get this n squared buildup. It becomes like a doubling crystal. You know, as you go make it twice as long, it's 4 times the amount of power, just from constructive interference with the field. Okay, there are 2 terms here. This one is the not quite going actually the speed of light term, and this is the unwiggling term. And since I showed you that K equals 1 is sort of the magic crossover to when you can start seeing this, you can see that you've got to include both these terms. They're comparable. Okay, so now we get to do all of this wonderful doing something periodically n times and adding it up coherently physics, which I think of as diffraction grating physics, or multiple slit diffraction pattern physics, right? It's basically just a diffraction grating equation. The electron slips one cycle per undulator period, so the length of a coherent pulse, the length of a pulse that you make, has to be at most n cycles long, where n is the number of periods. You slip one period every cycle. By the time you get out of the undulator, you've slipped n periods. You're creating a coherent pulse brain. Coherent means the phase at the front tells you what the phase at the back is. What is that distance from front to back? It's got to be capital N, the number of periods. So you've kind of constructed a pulse that has a certain length. Okay, that's called the coherence length. The highest field, that is the best opportunity to get this coherent addition, happens if you're exactly on the resonance. Okay, so if you're not quite on the resonance, how does it go? Well, it goes like a diffraction grating. It goes like a nice little Fraunhofer thing. You can be very unlucky and get destructive interference over exactly adding up over the n periods, or maybe you could get unlucky in other places, but basically it falls off like this. Okay, now it's only a few minutes into this talk. About 15 minutes into this talk, and I've already explained, and we already now know the undulator resonance condition. That turns out to be exactly the same as the free electron laser resonance condition. They're the same. So now you know what color will come out. This 1 over gamma squared is the color that will come out. The undulator bandwidth, explained, just depends on how long the undulator is. Want to have narrower bandwidth, just build a longer undulator. The photons come out diffraction limited if they're within that cone, if you have a small k. So what's different between just the way an undulator works, which have been around since the mid-1990s, like the advanced photon source, is filled with undulators. What's the difference in an FEL? The difference is something having to do with coherence between electrons. Okay? So here, this tells the story. Here's the undulator condition for a single electron. Photons produced on different undulator bends, but from the same electron, are in phase. That's the condition that we just derived, okay? Here's the problem. Here's what my electron bunch looks like. These electrons are all in different places. The photons from different electrons are out of phase. A problem, right? Now, okay, maybe it's not a very big problem, because after all, each electron is going to be producing this really powerful burst of radiation, scaling like n squared, right? Unfortunately, not right. Undulators are actually weak radiators, so although you get this wonderful classical buildup, the number of photons per electron at the end of an APS standard undulator is about 1/100th of a photon. In other words, an electron goes through 100 of those, you know, roughly the number that they're on the whole ring, roughly, okay, before it emits a photon. One photon. So you aren't going to make a laser that way. However, there's this really interesting little thing that people in the field of radiation know, because it's so important for microwaves, magnetrons, things like that. Okay? And that is that if you change the wavelength of the radiation, you can eventually get all of the particles that are in your bunch radiating to radiate in phase. And it's not very mysterious how that happens. It's basically the way a classical antenna works, where the current in an antenna has lots of electrons, right? They are not coherently related to each other. However, they are all within a small fraction of the wavelength of the radiation, and so they radiate in phase. It's just, that's a classical thing. A bunch of classical sources, they will radiate in phase under that condition. So here you get, for a bunch of electrons, you get to go from the power radiated by each electron times the number of electrons. You get to go to that amount of power times n squared just by changing the wavelength. And n, I said, was about, I think maybe I didn't say it was written there, it was about 1 billion, typically. You know, we talk about a nanocoulomb as a good, healthy bunch of electrons. We work with smaller amounts of, you know, a few picocoulomb, a few hundred picocoulombs. Not much smaller than about 20 picocoulombs. That's a very weak bunch for us. So that is billion, and that's a lot. N squared can be a lot. So how do we get this bunch of electrons to turn into a free electron laser? Well, we could make the wavelength of the free electron laser longer, and then, you know, then you get a microwave tube. Or we could get them to microbunch so that their density fluctuates, so that they're all lined up on successive cycles. And that's actually what we do. How do we microbunch? Well, here's the great thing. This is why, you know, this is why FELs happen. I mean, if microbunching was a really difficult technical thing, I wouldn't even be talking about it. Here's the reason that free electron lasers exist in this era, because microbunching happens by itself. It happens by itself. It's a self-organized thing. They will find a way to microbunch. Once they begin to feel their own radiation. This is where the quantum theory starts. You start thinking, stimulated. They're starting to feel their own radiation. This is where the stimulated comes in. So let's see how that happens. Okay, here's an undulator. Plus, minus, these are the directions of the field, okay? Magnetic field. There's that undulator equation again. And here's the wiggling electron, okay? Now, there's K over gamma, the deflection angle. Okay, now, let's say that the electron is coming along, and when it reaches this point where it's feeling a large deviation in its motion, the electric field is pointing in the same direction as the instantaneous transverse velocity of the electron. So the electron is going around, it's wiggling the magnetic field. There's also an electromagnetic field around from previous synchrotron radiations or of other electrons. And And it happens that they add up, the force adds up. So then I get a little extra pull at the point when I'm getting my maximum deviation from the magnetic field. Okay? Now, I happen to be in resonance. Of course, 1.5 cycle later, both of those have reversed. 1 cycle later, both of them have reversed again. Both the electric field of the radiation and the direction, the transverse direction, that got reversed. They stay in phase, and therefore you get coherent addition of the force exerted by the radiation itself on the electron. Okay? Now, what I've actually described is loss. You thought I was describing gain. But I've described a situation where the electron gets more energy from the field. Of course, that's loss. We call gain when the field gets the energy. But you could have the opposite situation too. Some electrons lose energy, others gain. And so the energy is modulated at the resonant frequency. Some gain, if they're in a slightly different place, they happen to lose. And so at that resonant frequency, you get a modulation in energy. Okay? Now, here's the really cool thing about this response. I explained to you that the electrons are all going the speed of light, or as close as hardly makes a difference. That's true, but they're not going in a straight line. So what happens when they get this extra kick is they start changing their orbit. Well, once they change their orbit, they start lagging behind or leading the resonance. It's a little bit counterintuitive, but if I kick it a little harder, it'll make a larger orbit, it'll come back later, it'll lag the radiation. It'll start to lag behind it. On the other hand, if the electric field was countered, then I kick it a little bit less hard, or I counter the motion of the magnetic field, it'll undergo a smaller orbit, and then it'll come back center. So there's this lagging leading stuff that leads to micro bunching. The actual density starts to bunch up every cycle. Okay? Micro-bunched beam then will radiate coherently once it gets micro-bunched enough. So, in a free electron laser, you have that situation where electrons eventually get bunched, and then they start radiating. And in a simulation, which I'll show you a little bit better example of later, you can see this happening in the density in the co-moving rest frame of the electron. That's the resonant frequency. And the radiation intensity then should go like n squared for n, the number in the microbunch. Okay, so now that you know the basic principles, let's look at how we can turn it into a laser that we can use. Well, the original way that John Mady, actually this was invented at Stanford. Did I neglect to mention that? Long time ago. By Mady, and his original idea was, well, he's the laser guy, right? His original idea is, let's put it in some mirrors, and let's build a resonant cavity where the cavity resonance matches the FEL resonance, and we'll get alpha radiation. That's certainly one way, and that way worked at Stanford for areas where you had good mirrors and good control over the cavity. You could also just build a seated amplifier where you input radiation that you made some other way, maybe this way or maybe just with the conventional laser, but it happens to be on resonance and it gets amplified. Or you can just make the undulator really, really, really long. If you do that, then the radiation that you produce that's just spontaneous undulator radiation at the beginning of a very long undulator will start to kind of build up, and if it happens to be at the right color, right in resonance, it'll start to build up coherently and take over. That process is something that we in the laser business have forever called amplified spontaneous emission, or ASE, but the accelerator people decided that they would call it self-amplified spontaneous emission, or SASE. So you can tell whether you're talking about X-ray FELs or any other kind of a laser by whether you include or drop the S, but it's the same. It's the same thing. And notice that this doesn't require input radiation or mirrors, so it's very good for X-ray regimes where you don't have good optics. Okay, so a few other little nuances here before I get to the actual. Before I get to the actual FEL. Some electrons accelerate at every cycle, and when they accelerate at every cycle, that's loss, because it's loss of X-ray power. Some decelerate at every cycle, that's gain of X-ray power. Okay, and so you've got to balance loss and gain, and you want rather have gain win. That's your gain. Your goal is to have it be gain, not loss, right? Not both. So gain is a trade-off between detuning and spontaneous undulator power. So what you would really like is electrons to naturally move towards the resonance as they undergo the FEL process. That would be better than if they started on the resonance and then either gained or lost after that. So Medy's theorem is exactly that. Don't tune on resonance, tune a little off. Not all the way off this curve, about halfway off. Actually, if you take the derivative of this curve and look at the peak of the derivative, that's the best gain. Okay, now let's talk a little bit about this bunching process and how it gets started. Which electrons are going to be the ones, the lucky ones, that happen to be responsible for seeding the microbunching, and which ones aren't? Well, this depends on where the electrons are. The kth electron produces a field with its own particular phase, and then those fields just superpose. So I can add them. There they are. They're just added up. And there's a whole bunch of them, so I'll divide by the number of them and create a dimensionless parameter. This is called the bunching parameter. If the bunching parameter is 0, it means that my electrons are perfectly uniform, and the fields add to 0, and it's going to be really difficult to make a laser. If B equals 1, they're perfectly bunched. There's constructive interference, and I've already made a laser. If B equals in between, they're randomly distributed, and that's the normal for us, for the normal situation for FEL SASE operation. The undulator radiation starts up from noise. Noise means just the random fluctuations that produce spontaneous emission of undulator radiation in the FEL. And then the modulation of energy gives rise to modulation of density. You have an exponential growth phase, and eventually you get really good microbenching, then you get saturation at sufficiently high power. And here's a simulation by Sven Reicke at UCLA that shows this in the co-moving frame. Those electrons are being in the process of going through a long undulator and being bunched. You can see it happening now. They are microbunched. Now look. They start to kind of trail off on one side. You see that? What's that? That's...
So the vertical motion is the...
the vertical motion is because it's a true 3D simulation and you have to put in focusing particles every so often to keep the electrons.
So that's the wiggling motion.
So that is not the wiggling motion. The wiggling motion you can't see, it's too small. The big breathing, I'm sorry, I should have said, the big breathing, don't worry about it, it's part of the simulation. It is something you have to worry about in beam physics to keep the beam together. Okay? But the main thing you have to worry about is what's happening longitudinally. And they are starting to bunch because some are getting sped up and some are getting slowed down through this wiggling. And then when they get maximally bunched, you get a big burst of coherent radiation, and the electrons all lose energy. It is not a small interaction anymore. I said that undulator radiation is weak radiation. You hardly notice that the electron changes energy when it radiates 1 photon, 1 kilovolt photon, and it's a 6 GeV electron. Okay, but this collective effect is so large that all of the electrons begin to lose significant amounts of energy. You can even see that in the simulation.
So does that mean their repulsion becomes more important?
No, they're so stiff. These electrons have effective masses with respect to electron repulsion in the lab frame of 30,000 electron masses. So no, and they get through the end of it pretty fast. Okay, so here's a little simulation done by some of those people, Giron and company, and you can see the exponential growth regime. This is for LCLS properties, and you can see the saturation. This is power on log scale. Every decade is pretty close together, so it's a huge increase. What's more interesting is to look at how the microbunching affects the light. Now let's take a look at the spontaneously and stimulated emission coming from the end of the undulator. If you looked right here, if you stopped your undulator right here, it would look quite random. And this scale here is time in femtoseconds. 0 femtoseconds is here, 1 femtosecond is way over here, 2 femtoseconds way over there. So this is a 2.5 femtosecond scale. If you go into this exponential regime, you begin to see that the organization of microbunching has led to certain